In this problem, we are given a flange bolt coupling consists of 6 10mm diameter steel bolts around a bolt circle of 300mm in diameter and 4 20mm diameter aluminum bolts on a concentric bolt circle of 200mm in diameter. We are tasked to find the torque that can be applied without exceeding a shearing stress of 60 megapascals in steel or 40 megapascals in the aluminum, using a shear modulus of 83 gigapascals and a shear modulus of aluminum equal to 25 gigapascals. To solve this problem, let us write down the known givens. For the outer circle made of steel, we have 6 bolts with a diameter equal to 10 millimeters. That has a mean radius equal to 300 divided by 2, that's 150 millimeters. And a shearing stress that should not be exceed 60 megapascals with a shear modulus equal to 83 gigapascals. And for the aluminum bolt, we have 4 bolts with a diameter equal to 20 millimeters. That is a mean radius of 200 divided by 2. This is 100 millimeters. And a shearing stress that should not be exceeded of 40 megapascals with a shear modulus equal to 25 gigapascals. And to solve this problem, let us assume that aluminum will have the maximum shearing stress of 40 megapascals. And to solve for the force in aluminum, we multiply the shearing stress of 40 megapascals by the area of the bolt, that is equal to pi times 20 millimeters squared divided by 4. So the force that is applied on the aluminum, that is equal to 40 times pi 20 squared divided by 4, that is 4000 pi. And by a ratio and proportion of the force in aluminum to its mean radius, it is equal to the force felt by steel divided by the mean radius. So for aluminum, that's 4000. Its mean radius is 100, and this is the force applied on steel divided by the mean radius of 100 millimeters. No, that's 150 millimeters. And we can solve for the force that is felt on steel, that is 4000 pi divided by 100, cross multiplying. This is multiplied by 150. And the force felt by steel, that is 6000. And let's try to check if it exceeds its shearing stress of 60 megapascal. We divide this by the area of steel, that is pi times the diameter squared divided by 4. So 6000 pi divided by pi 10 squared all over 4. It has a shearing stress of 240, which exceeded its capacity. Therefore, our assumption that aluminum yields first is incorrect. So let's try to assume for steel will first exceed its limit. So for steel, to get the force felt by steel, we multiply the shearing force of 60 megapascals to its area. That is pi d squared all over 4. And we get the force felt by steel, that is 60 times pi 10 squared all over 4. We get 1500 pi. And for the force felt by aluminum, by utilizing ratio and proportion to its mean radius, we have steel that is equal to 1500 pi all over the mean radius of 150 equal to force felt by aluminum all over its mean radius. So we have force felt by aluminum equal to 1000 pi. And let's try to check if this exceeds its shearing stress capacity. We divide the force felt by aluminum to its area. So you have 1000 pi all over pi times 10 squared all over 4. The diameter for aluminum is not 10, that's 20. This is the stress felt by aluminum, which is equal to 10, and it does not exceed its capacity of 40 megapascals. Therefore, the force felt by steel and aluminum does not exceed its capacity, that is equal to 1500 pi for steel and 1000 pi for aluminum. Now we can solve for the torque that is applied. That is equal to force felt by steel times its mean radius times the number of bolts plus the force felt by aluminum multiplied by its mean radius times the number of bolts. We have T equal to 1500 pi times the mean radius of 1050 millimeters times the number of bolts, that is 6, plus the force felt by aluminum, that's 1000 pi. Also, the unit for the force is in newtons. So let's put newtons here and newtons here, times its mean radius of 100 millimeters multiplied by the number of bolts. We get torque in terms of newton millimeter, that is equal to 1500 pi times 150 times 6 plus 1000 pi plus 100 times 4, which is equal to 545,497,787.14 Newton millimeters. And if you want this to convert into kilonewton per meter, let's multiply this by a conversion factor of 1 kilonewton per 1000 newton to cancel newtons, and multiply this by 1 meter per 1000 millimeters to cancel millimeters. We get torque equal to 1 over 1000 times 1 over 1000. That is equal to 5.49 or 5.5 kilonewton meter. And that's our final answer. So this must be a typo. This should be 5.49 kilonewton meter.